So this is the first video for chapter 1, which is Introduction, Matter, Energy, and Measurements. So with chapter 1 and with all of our chapters this semester, there will be multiple videos for each chapter. There's just too much information to put in one. These videos are not always going to be the same length, but I've kind of divided them up based on the easiest stopping points. So this first one is an introduction to chemistry a little bit, scientific method, because this is a science class, we have to talk about that for at least 30 seconds, and then starting categorizing matter. So for this video, we're just looking at the matter component. So chemistry. I usually give a lovely long speech about why chemistry is obviously the best science. You're all in this class because you're pursuing something related to science. I know that might not be chemistry. It could be that you're pursuing biology or engineering or medical school or dental school or pharmacy. You could be going into physics. It could be a whole lot of things. But chemistry is important for all of them. It's considered the central science. If you look at the name of our textbook, it's actually called Chemistry, the Central Science, because all of the other branches of science interact with chemistry. So other than the fact that whatever thing you're interested into pursuing, so like if you want to be an engineer, it's the engineers that told you had to take this class. It wasn't the chemists. We didn't say who had to take chemistry. It was your major. The people that are experts in the field that you were wanting to pursue told you that you needed to take chemistry, or else it wouldn't be on your requirements for your degree. So obviously it's important for those reasons, and you may not know what those reasons are yet because you're maybe not far enough into your major to understand what parts of chemistry are going to be important. But looking outside of that, chemistry helps you understand the world around you. So it's going to answer all these kinds of fun questions that are things that you deal with all the time. Like why ice melts, why leaves change colors in the fall, and then how batteries work, how we get electricity out of batteries, and why certain metals rust and other ones don't. All kinds of everyday kinds of questions that you'll have answers to. And the answers that you'll have will be more than just, Googling it off of Bob's page of random facts, which may or may not be true, but you'll maybe, hopefully, at the end of this, understand the science behind it. So all of these are related to chemistry. Okay, so based on our textbook, the definition of chemistry is the study of matter and the changes that matter undergoes. So I have to back up and give you a definition of matter for this to make sense. Matter is anything that has mass and takes up space. So basically, it's anything that exists, like that we could make some sort of mass or volume measurement of. So chemistry is the study of everything that exists and the changes that it undergoes. Wow, buddies, that's a big, broad category. We're going to have to narrow that down. Okay, so, and that's what this first video, we're going to look at narrowing down matter into smaller subgroups so it's a little bit more manageable and not so abstract and huge and giant and never able to figure out. Okay, so before we jump into the matter thing, we've got to talk through the scientific method. And this is a science class, so we have to. So the scientific method is just a systematic way scientists approach learning about the world, solving problems, and coming up with statements or explanations about how things happen in the world. So as a scientist, we start by collecting information, making observations, seeing things, doing experiments that based on that information that we've collected leads us to a hypothesis, which is a statement that we're wanting to prove or disprove about it being true. And then we're going to test that hypothesis. So testing that hypothesis, we're going to set up experiments deliberately designed to tell if our hypothesis is true or false. And we're going to have to do those experiments many times. So we're going to test our hypothesis and then come up with a theory based on our results and our hypothesis. What did we learn about this? And then we're going to continue to test that theory, that hypothesis that has kind of moved to the next stage, and modify it as needed. Now, the big thing with this is understanding that scientists just don't make statements and just move on. Scientists have to have a lot of experimental evidence behind any sort of statement or determination that they've made. It's not just, hey, I feel like this is true, so I'm going to say it and it's going to be real. In science, in order for a scientist to publish something, so publish it in an academic journal, so put it out there in the world so that way it's, hey, look, I'm a scientist, this is what I've been doing in my lab, these are the things that I've learned, and this could be in any branch of science. These experiments have to be peer reviewed, looked at by other scientists before they can be shown to the world as experiments and evidence for anything. I think that's just an important thing to know with the world, with the internet and all social media and everything, where people can say whatever they want. They can say what they feel. You can make outlandish statements. And a lot of people feel, well, how am I ever supposed to know what is real and what is not? Well, when it comes to science, there is a way to know what is more likely to be correct. Because with scientists, there's always the chance that you've done your experiment 3 million times, but you missed the one result, or you needed to do it 3,000,001 times before you found one result that looked weird. But you look at academic peer-reviewed journals. So there are places to find good information about science and ways to tell whether or not the thing that showed up on Facebook is real or if someone's just talking because that's how they feel. So I'll get off my soapbox here. So the other big thing I want to talk about are at the end of this one, it says that you formulate a theory and then you repeatedly test the theory. Well, at the end of the scientific method, there's actually two things that you can come up with. There can either be a scientific, again, this is like based on lots and lots and lots and lots and lots of many scientists, millions of data points. You can either come up with a scientific law or a theory. And there are some opinions of people that scientific laws are correct and theories are just guesses, and that's not at all true. Scientific laws and theories have the same amount of weight behind them. So before someone can call something a scientific law, so like the second law of thermodynamics, before it can have the word law in it, or the law of conservation of mass, which we'll talk about in this chapter. Before it can be considered a law, it has to have lots and lots and lots of evidence, lots of scientists that have looked at it with basically nothing showing that it is not correct. A scientific theory has to have the exact same amount of evidence. The only difference between them is how they're stated. A scientific law is a statement. It doesn't explain itself. The law of conservation of mass, which we'll see in the next video, says in a chemical reaction, matter is not created or destroyed. It's a statement. Bam. In a chemical reaction, this is what happens. And then it walks away. Mic drop, it's done. The statement just tells you what is true. It doesn't explain it. A scientific theory describes something. It is just as accurate, just as proven as a scientific law, but it's a description. And we'll also see theory. We're going to look in chapter 9, the valence shell electron pair repulsion theory. That will sound less scary later, I promise. But the theory is just an explanation. Okay, it's saying why something happens. A scientific law doesn't give you a background. It just says what is true and what is not. Depending on what we're looking at, like the scientists are looking at to try to get information, maybe it can come up with the scientific law. It can make a statement based on the evidence. We know that if this happens, or if we do this, this will happen. Bam, that's a law. They might not yet know the theory behind it. They might not know the why it happens. So the theory is still supported by the same amount of experimental evidence. So again, I'm just trying to make sure that we all understand that scientific laws and scientific theories, both of them are backed by experimental data. Both of them are backed by the same amount of proof. I'm doing finger quotes right now. So evidence. They're just different in how they're stated. A scientific law, straight up sentence, that's a statement. Theory. Let's explain why this happens. Okay. So theories are not less proven than laws. If anyone tries to tell you that, they are incorrect. And you, being a scientist, can then now explain to them the differences between laws and theories. Okay, so now we're moving into kind of the meat of chapter 1. We're looking at matter and sorting matter, which is everything that exists, into smaller categories. Okay, there are two different ways we can sort matter. But again, just a quick reminder, matter is anything in the physical, it's a physical material of the universe. So it has mass and occupies space. So you might think like, oh, okay, like so pencils and tables and chairs and people. Yeah, but smaller things than that too. Air is made up of molecules and those have mass and occupy space. So matter doesn't have to be giant things that we can see. It just has to have some sort of mass and um, volume. Okay, so these are just some examples. Pretty much everything is matter other than stuff like energy. That is not matter. We're going to be looking at their properties, and a property is just a characteristic. Okay, so I have a lot of Chuck Taylor Converse All-Star shoes. I have like 15 pairs of them. Just don't worry about it. I have a problem. And each of my pairs of shoes is a different color. And right now I've got on a pair that's red. So a property of my shoes are that it's red. So a property is just a characteristic. Okay, and ways we could sort based on that characteristic. So color was the example of a property that I've already used. Melting point, what temperature it needs to get to before it can go between solid and liquid, what it smells like, how large it is, how much it weighs. These are all properties. Okay, lots and lots and lots of different properties. So we're gonna classify matter. We're gonna break matter down into smaller groups, and there's two different ways we can classify matter. I'm getting ahead of myself. Before we get to classifying matter, we've got a couple of vocab words we have to learn. So atoms are tiny, tiny. They're always represented by little spheres, like a ball, okay, of matter. Now, they are not the smallest thing that exists. There are things smaller than atoms, and we're going to talk about those in chapter 2. But they're the smallest building blocks that that have a consistent set of properties. So if we get something smaller than an atom, we don't see properties. They're the smallest things that we can sort based on properties, basically. Okay. And molecules, or when we have two or more atoms joined together, bonded together, stuck together, smushed together. At this point in the semester, whatever you want to, however you want to explain that. So an atom is going to be represented visually for us by a sphere, and molecules are going to be multiple spheres smushed together. So in this example, that white atom in the atoms box is a hydrogen atom. And then the molecule in the molecules box is water, which has 2 hydrogens and 1 oxygen. So it's not that they're just near each other, but they're physically attached to each other. Okay, so it could be 2 atoms, it could be 47 atoms. I don't care how many atoms there are, but as long as there's 2 or more atoms stuck together, we have a molecule. Okay, so here's our 2 different ways that we're going to classify matter. One of them you're going to be much more familiar with than the other one. The first one, I'm not thinking it's going to take a lot of work to get you guys able to classify matter. The first is by physical state, and by physical state I mean solid, liquid, or gas. There are more physical states, but those are the 3 that we are focused on in this course. So we could take matter, stuff that exists, and put it in the category of it's either a solid or a liquid or a gas. Okay, that's the first way we could sort matter. The second way is by chemical composition, and we're going to spend more time on that in this video. So we're going to start with the physical state one, because again, I feel like you guys are going to be all right with this. So the 3 states of matter that we're looking at are solid, liquid, and gas. In this image, we've got glaciers, which are ice, which are a solid H2O. We've got liquid water, so a liquid H2O, and then in the air we have clouds, which are made up of gaseous H2O, and just in the air we have gaseous H2O. So you've seen water in all of its states. I know you may not, you could say maybe I haven't seen water as the gas state, but you're around it right now. It's in the room with you. There's water vapor. That's what humidity is. So the thing that I want us to look at are down here. It's showing us what the molecules, how the molecules differ in the solid state versus the liquid state versus the gas state. And honestly, this gas state picture drives me up the wall. If that was the circle, here's my water molecule. In that amount of space, there'd only be one. So, backtracking. Solids. The atoms and molecules are very close together, and if it's a crystalline solid, it has a definite pattern. And these solid atoms or molecules, in this case they're molecules because we're looking at water, these molecules, it's kind of like their feet are glued to the floor, so they're not able to move very much. They can kind of wiggle back and forth. So if your feet were glued to the floor, you could kind of wiggle back and forth and front and back. But if you wiggle too much, you'd fall over. And these molecules can't fall over. They can just wiggle a little bit side to side. They don't have a lot of motion. They don't have a lot of movement. Liquid molecules are also super close together, but you can see they're disorganized. These liquid molecules are able to move. They have some kinetic energy. They're able to move, but they're still stuck staying very close together. So they're not in a nice, pretty organized pattern. They're kind of just a cluster of molecules doing their thing, but they're all very, very close together. So solids and liquids, the atoms or molecules, depending on what we're looking at, are very, very close together. In a gas, the atoms and molecules are super far apart. That's why I don't like this circle, because it shows them way too close together. It would be like there's a water molecule and he can't see any of his neighboring water molecules because they're so far away. So gaseous atoms, it's like they're super rural. They've got, there's a house and then you don't have a neighbor for 6 miles. That would be gas molecules. Liquid and solids, they're much closer together. We're thinking like they're living in an apartment complex. They're super close together. Okay. So just looking at these in a little bit more detail. Something in the gas state, if something is a gas, it does not have a fixed volume or shape. Its volume and shape are whatever the container that it's in. So if you have a square box that you filled up with a gas, then the volume of the gas is whatever the volume of the box is. And the shape of the gas would be the shape of the square box. Okay. And then if you take that gas and you move it into a container that is much smaller and it's shaped like a sphere, so it's like a ball, its volume and its shape both just changed. Gases fit their container, whatever volume and shape that is. So they don't have their own set volume or shape. Liquids have a very set volume, but they can change their shape. So think about if you've ever used a liquid measuring cup, like those glass cups with a little handle on it that say like 1 cup, 2 cup, 3 cups, however big yours is. And if you've ever made anything where you had to measure that out. So like if you've used a box cake and you have to measure out the oil and the water, you measure out the oil in the glass measuring cup. Like let's say you need a cup or 1.5 cups. So you pour the oil into the measuring cup to 1.5. So its volume is 1.5 cups. Okay. But its shape is just the shape of that. Now, when you pour it into the bowl with the cake mix, its volume is still 1.5 cups. We're relying on the fact that when I measured it out in the measuring cup, that the volume in the measuring cup is the same volume when I pour it into something else. That's the point of the measuring cup. But the shape is it's gonna mix in with the cake mix. It's gonna go to the bottom of the bowl, whatever. So liquids have a set volume, but no set shape. Solids, on the other hand, have a very set shape and a very set volume. Baby, wait. Griffin, wait, baby, please. So I just got to have another example of liquids having a distinct volume but no set shape because my 2 kiddos just spilled a big cup of water all over the floor. And I know that the amount of liquid that I had to wipe up off the floor was the same volume as the amount of liquid that was in that nice full cup. So, sorry, that just made me giggle, so I decided to share with you guys. So, hopefully we're feeling okay with the solid, liquid, gas scenario. So questions that you'll be asked with this are likely going to be kind of like matching type questions. Hey, here's, like cooking oil, is it a solid, liquid, or gas? Well, it's a liquid. Sugar crystals, is it a solid, liquid, or gas? Well, they're solids. So those kinds of things. Or I could ask questions about describe, the shape versus volume for each of these 3 things. Okay. So here's just another picture kind of summarizing all of that. The only new addition is that we know that if something is in the liquid state of matter, that doesn't mean that that's the only state of matter that it will ever exist in. Like the picture that we started with was H2O, which we typically call water, in a solid state, the liquid state, and the gas state. So we know it can be in all 3. In order to change between states of matter, heat is the component that changes, that we have to either add heat or remove heat to change something from a solid to a liquid to a gas, or vice versa. So based on your everyday experiences, I have a feeling you have a decent grasp on this. If you've got liquid water and you need to boil it to make it become a gas, we have to put it on the stove or on the hot plate or on the fire. We have to heat it up. We have to add heat to it. You've got a solid and you want to melt it. You also have to add heat to it. If you've got a liquid like water and you want to freeze it into a solid, you need to cool it off. So we put it in the freezer, which releases heat or it cools down. So this is everything on this slide we've talked about already. It's just the addition of the heat being added or released, things being heated or cooled down to change between states of matter. Okay, so now we're on to our second way to classify matter, and this one's based on composition. Okay, so here in a second I'm going to draw us a nice pretty picture, but all matter can be broken down into two big subcategories. And the first of the big subcategories are pure substances. Pure substances are actually not a common thing for us to run into in the world, but pure substances are matter that has a distinct set of properties. And if we have one sample of a type of pure substance and another sample of a type of pure substance, they will be the same. So if I had a sample of pure gold, now I'm going to bet you've never encountered a sample of pure gold. Gold jewelry has a carat ranking on it, right? And so what that tells you is, or it gives you an idea of the ratio of gold to other elements mixed in it. So if I had a pure chunk of gold, like we took a big rock out of the ground and had gold in it, and we cleaned off all the other junk from it, and it would be pure gold. If I had another chunk of pure gold, both of those chunks of pure gold would have the same color. They would have the same smell. They would have the same melting point. They would have the same density. They would have the same set of properties. So we could tell that they were the same. Okay, so a pure substance, it's been reduced down to being just one thing. It's made up of entirely one thing. So the examples I used here are actually horrible examples because these on an everyday basis are not pure substances for us. Our tap water, when it goes to the water processing plant, they add fluoride to it. There's sodium in there, there's calcium and magnesium. There's all kinds of cations and anions. There's a lot of other things mixed in with our tap water. So our tap water is not actually a pure substance because it's not just H2O. There's other stuff mixed in with it. Table salt. Well, most table salt is iodized salt. If you've ever seen that on the container, that means it contains something iodide, usually potassium iodide. So it's not pure sodium chloride. And again, my example for gold is yes, pure gold exists. It's just you probably haven't run into it. So again, you don't run into a lot of pure substances on a day-to-day basis. It's actually very rare to run into a pure substance. They exist. Oh my gosh, they exist. But most of the things we deal with are not. So if we're looking at pure substances, that category can be broken into two smaller subcategories underneath pure substances, and that's elements or compounds. So both of these are pure substances. An element is a pure substance and a compound is a pure substance. So an element, we can't break it down into smaller things and it have a set of composition, a set of properties. So we only have one type of atom. So when we were looking at the picture of the atom and the molecule earlier, there was a white sphere that I said was hydrogen. And then there was a molecule that had two white ones and a red one, and I said that was water. So an element, based on the pictures that we're looking at, would be a different color of atom. So every color of atom is its own element. There are 118 elements that we currently know about. So if we were really going through this color thing, we'd have to have 118 different colors, and each atom would have its own color. In real life, these elements don't necessarily all have different colors, but they are unique from each other. We're going to look at these elements in a lot more detail in Chapter 2. Compounds. Okay, compounds are made up of at least two different types of elements. So they are molecules that have at least two different types of elements inside of them. But molecules and compounds are not the same thing, necessarily. So a molecule, the picture that I showed earlier we talked about, was when you have two or more atoms stuck together. But I didn't make any sort of statement about what types of atoms they could be. I could have two atoms of the same element. I could have four atoms of the same element, and that would be a molecule. For something to be a compound, it's going to be a molecule. There's going to be more than one atom, but it very clearly has to have at least two different types of elements. So water has hydrogens and oxygens in it. So it is a compound and a molecule. It's a molecule because there's three atoms stuck together. It's a compound because there's two different elements, hydrogens and oxygens, involved. Okay, so what I would normally be doing right now is writing on the board as we go through this. So I'm going to put it up here. So matter, we're trying to sort matter I'm going to break it down into two big subcategories. I want a different color. Okay, so what we've talked about so far are pure substances. So matter can be broken down into pure substances or something else, and we'll get to that something else later. Within that pure substance category, actually, I'm going to make my lines red. We have elements and we have compounds. Okay, so elements, one type of atom. There's only one type of atom. Compounds, two types of atoms, two different elements that are stuck together into a molecule. So the only way for me to turn a compound into an element, if I were wanting to do that, that would have to be some sort of chemical reaction. I can't take water and just pull out the hydrogens and separate them from the oxygens. You have to do some sort of chemical reaction. So elements are, in this table, the simplest thing. Okay, now we're going to come back and I'm going to add stuff to the other side, but for now, we know that one category of matter we can decide if it's a pure substance, and then once we know it's a pure substance, we can separate it further down into an element, which is just one type of atom, or a compound, which have at least two different types of elements, two different types of atoms in there. Okay. So this picture hopefully will help you visually, especially with the molecule compound scenario. So in image A, in this one, we only see one color, which again is the visual representation of one type of element, and all of the atoms are alone. So these are just atoms of an element. They're all the same color, so they're all the same element, and they're all alone, so they're not a molecule. They're just an atom. In picture B, I only see one color. I just see blue. Okay, so we only have one element. Now, these blue atoms are grouped in sets of two, so there are two atoms stuck together. That makes this a molecule because I have two atoms. The definition of a molecule, two or more atoms stuck together. I have two atoms stuck together, so I have molecules, but they're all the same element, so it's molecules of an element. In scenario 3, in picture C, I definitely have molecules because it looks like everything is four atoms stuck together. Three green ones and one purple one. The fact that there are two different colors involved is what makes it a compound. A compound is when we have at least two different elements, which again, visually are going to be different colors. So compounds are always molecules. Molecules are not always compounds, right? Notice in the compound picture, it also says molecules. Picture C. In picture B, they're molecules, but it's not a compound. So molecules, two or more atoms stuck together. Compound is more specific. Two or more atoms stuck together, where we have at least two different elements that are part of that stuck together thing. So hopefully that helps. So we're going to look at a little bit more detail with elements and compounds, and then we're going to come back and look at that whole other side of the chart. So like I said earlier, there are 118 elements that we currently know about. The last, I don't know, what is it, 15 or so have been created in a particle accelerator, have been created in a lab, but they're still just different types of elements. They occur in varying abundances, so that means the amounts that we can find on our planet and in our body. So this is not a thing to memorize, but I just think it's super interesting. So if we look at our planet and we look at the crust, so not the water part, just the land part of our planet, there are 118 different elements, but our planet, the land part of our planet, about half of all the elements found on the land part of our planet are oxygen. One element out of those 118 makes up half of it. The next most abundant is silicon, which is about 25%. So silicon and oxygen together form sand. So there's a lot of sand. Okay. Then the next most abundant element is aluminum, then iron, then calcium, and then all of the other elements add together to be 9% of the rest of our planet, the land part. Now, in a human being, oxygen is the most abundant element, just like it is on the planet, but it's 65%. The next most abundant element is carbon, which didn't even make the pie chart for the planet. And then hydrogen also didn't make the pie chart for the planet, and then all the others. Okay, so again, not something to memorize, but just because there's 118 elements that exist doesn't mean we have equal amounts of all of them. Some of these elements do not exist naturally. We have to create them in the lab. So just again, I thought interesting. Okay. So each element has its own name and its own symbol. The symbol is either 1 or 2 letters long. So with 118 of them, we couldn't just give every element its own 1-letter symbol. We only have, so many letters in the alphabet. So 1 or 2 letters long. The first letter is always capitalized. If there's only 1 letter that's its symbol, it's a capital letter. If there are 2 letters, the first one's capitalized, the second one is lowercase. Okay. So if you're somebody who writes everything in all caps or all in lowercase, you got to stop that right now, my friends. In chemistry, you need to make sure that I can tell if it is a capital or a lowercase letter. Okay. And I just have some of the most commonly used elements listed here. In chapter 2, we're going to spend a lot more time with these elements. A lot of their symbols make sense. So carbon, its symbol is C. Nice. Hydrogen, it's H. Beautiful. Nitrogen, it's N. Glorious. And then some of them don't seem to make sense at all. So tin is SN. Sodium is Na. And sodium, there's neither an N or an A in the word sodium, but their symbols came from their original name, which has been translated into the names that we're used to. So sodium was not the original name of the element. It was natrium, which Na was the first 2 letters, so it made a lot of sense. So some of the element names and symbols we're just going to have to memorize. They don't seem to make sense. They used to make sense. We're the weirdos that translated them. So again, in chapter 2, we'll deal with that more. But these are just some of the most commonly used elements. Notice in all these scenarios, the first letter is a capital letter. If there's only 1 letter, it's a capital. If there are 2, the second letter is always lowercase. One that's not listed here is cobalt. Cobalt has a symbol of Co. Okay, so that represents the element cobalt. It's important that we can see the capital letter C, the lowercase letter O, because if I write it like this, that tells me that I have carbon and oxygen together in a molecule, which is carbon monoxide, because carbon, capital letter C, oxygen, capital letter O. So capital letters and lowercase letters are super important. Cobalt is a metal. Carbon monoxide is a toxic gas. So we don't want to get these things confused. Okay, so 118 elements, they all have names and symbols. Compounds. Compounds are, again, 2 or more atoms stuck together with at least 2 different types of elements. So the example that I used earlier was water, which has oxygen and hydrogen in it. Okay. So some elements exist as diatomic molecules. Now notice this is a molecule, but not a compound. This is a molecule, but not a compound. Just pointing that out because up here I have them written as individuals, and in real life they would have looked like this. But when we take, let's go with 2 elements and put them together to make a compound. The compound that we make is brand new. It's not like, so the mommy and the daddy made a baby, and the baby looks a little bit like the mommy and a little bit like the daddy. You know how that works with biology stuff? Well, we're in chemistry, my friends. We're not in biology. When hydrogen and oxygen come together to make water, water doesn't become a little bit like hydrogen and a little bit like oxygen. It makes its own thing. Okay, so these are just a set of properties about comparing water to hydrogen and oxygen. Very different. My favorite scenario, though, is actually sodium, chlorine, and sodium chloride. So sodium, this buddy, is a metal, so it's shiny. It's kind of a silver in color. It is very reactive. Like if I buy some sodium from the chemical supply store, it is shipped to me in a bottle filled with oil where the sodium is inside that oil. Because if we take that sodium out and let it be exposed to the air, it starts reacting immediately with the water vapor in the air. So it's so reactive that it can't touch air. Okay. So it would be very bad for you if you were to eat it because we're mostly made up of water, right? And it reacts with water. So sodium, bad for you. It's toxic if you were to eat it. It's a shiny, very reactive metal. It's soft. You can smush it with your fingers. Okay, so sodium. Chlorine. Chlorine exists naturally as Cl2. It's a diatomic molecule. It is a yellow gas. We use it as a disinfectant at very low concentrations because it's toxic at much higher concentrations. So chlorine can kill you. Okay, it's toxic to humans. It's a yellow gas. Sodium chloride. That's table salt. We put it on our food because it makes it taste better. So sodium by itself as a pure element would kill us. Chlorine by itself as a pure element would kill us. Sodium chloride tastes yummy, so we put it on stuff. When you make a compound, it's its own thing. It has its own set of properties. It's not directly related to the two elements that made it up. Okay, so we're going to deal with that more later in the chapter or later in the semester, but just wanted to point that out. So now we're ready for the other half of our chart. So things can either be pure substances, which are elements or compounds, or they can be mixtures. Mixtures, two or more pure substances that are in the same container. So I take gold and like pure gold, and I take pure water, and I put the pure gold and the pure water in the same container. I just made a mixture. So mixture, two or more things that happen to just be in the same container. But the water and the gold didn't come together and make some magic gold water molecule. They're still their own things. They just happen to be in the same container. Okay. So in a mixture, each thing you mix together is called a component. So water is a component and gold is a component. Okay. So salt water. Salt water. It's made up of water and sodium chloride, salt. But we can separate those. I could boil out the water and the salt would be left. So mixtures, we don't have to do a chemical reaction. If I had the gold and the water thing, can you think of a way that I could take liquid water and solid gold, put them in the same container, and then how could I separate them back out? Well, that one, you pour the water out. Like you can separate them back into their individual components because all you did was put them in the same container. You didn't react them, they didn't make something new, you just put them in the same container. Okay, so there are two different types of mixtures. Heterogeneous or heterogeneous, if you want to say it that way. Heterogeneous mixtures, that's usually the way I say that, are mixtures that are not evenly mixed. So if I take sand and water and put them in a bucket, so I take some sand from the beach and I plop it in the bucket, and then I pour some water on top of that. They're going to arrange themselves where the sand's going to sink to the bottom. Okay, so the top of the bucket looks different than the bottom of the bucket, which looks different than the middle of the bucket. So that's a heterogeneous mixture. When I mix them together, they didn't evenly mix. They made layers, pretty much. Like oil and water make layers when you mix them together. The other option is a homogeneous mixture or homogeneous. A homogeneous mixture, it's evenly mixed throughout. So if you make Kool-Aid, so you take your pitcher, and let's go with, I have the Kool-Aid where the sugar's already mixed in. So I scoop in my Kool-Aid mix. And then I put in the amount of water from the sink that they tell me to, and then I stir it up real good with my spoon. That has a bunch of things in it. That's got water in it, it's got sugar, it's got whatever's in the Kool-Aid. And when I stirred it all up, when I drink out of that pitcher, hopefully the first glass of Kool-Aid will taste the same as the second glass of Kool-Aid, which will taste the same as the third and the fourth and the fifth. Like it's all going to be the same. It was a homogeneous mixture. They all were evenly mixed. Okay. Gases automatically go to this homogeneous mixture. So the term we're actually going to use after chapter 1 are solutions. Something that's a solution is automatically a homogeneous mixture. That's just another way to say the same thing. So I could redraw my thing here, but I'm going to actually be super lame and backtrack to right there. And we're going to add the two things we just learned. This one. So, all matter can be broken down into either pure substance or a mixture. If it's a mixture, I'm going to go down here so I have more space. We can then further break it down into two categories. It's either going to be a homogeneous mixture, evenly mixed, or it's going to be a heterogeneous mixture. Okay. So if I have a mixture, let's say I want to take my mixture and I want to turn it into, I want to separate it into its pure substances. I can do that in a physical way. So thinking back to the water and sand, how could I separate my heterogeneous mixture of sand and water back into just sand and just water? Can't I pour out the water? I'd have to dry the sand then as well. But these types of questions, I'm going to give you examples of matter and you're going to sort it into the different categories. So I'm going to get us back where we were. Okay. So these are the first three of these pictures we've already looked at. Okay, so just a reminder. First one, atoms of an element, and I know that it's just one element because they're all one color. I know they're atoms because they're just individual spheres. Second one, these are molecules of an element. We know it's an element because they're all the same color. They're molecules because I have groups of two or more, in this case two. This picture shows molecules of a compound. Molecules because I have two or more atoms, in this case 4 atoms stuck together. And I know it's a compound because I have purple and green. I have at least two different colors. Fourth picture, this is the visualization of a mixture. I have 3 different pure substances. This buddy is a pure substance, this buddy is a pure substance, this buddy is a pure substance. I know I have more of them. They're all in the same container. Do you see how they each look how they did when they were alone? But they're all in the same container. They didn't smush together and make a bigger molecule. They just happen to be hanging out together. Okay. Now from this picture, I couldn't really tell if this is a homogeneous or a heterogeneous mixture. I need a bigger picture on that. If I were trying to visualize a heterogeneous mixture, I would probably do something like put all of one kind on the bottom, like make layers. Basically what I'm trying to do here is, this is beautiful. I know my pictures are beautiful. Enjoy them. I'd make layers because then you know it's a heterogeneous mixture. If I was trying to visualize a homogeneous mixture, I'd probably make a pattern like orange, blue, green, and purple, orange, blue, green, and purple, orange, blue, green, and purple, just to show that they're evenly mixed. Okay. So this is the beautiful chart that the textbook came up with to help you sort things. If this is helpful, go for it. If not, that's also fine. But be prepared to sort matter into, is it a pure substance or a mixture? If it's a pure substance, break it down even further. Is it an element or a compound? If you decided it was a mixture, break it down even further. Is it a homogeneous mixture or a heterogeneous mixture? So on our discussion worksheet in our homework, these things are going to help you practice that.